Hello everyone. So welcome to today's class. This is Dr. Mahender, Associate Professor of Mathematics, B.V. Raj Institute of Technology, Narsapur. The course name is Linear Algebra and Calculus. The today's topic is diagonalization of a square matrix. So before going to today's class, just I will recall the previous lectures, what I covered in the previous class. So we computed then how to find the eigenvalues and eigenvector of a square matrices. Now today we will discuss one of the important concept is diagonalization of a square matrix. So this is very important in the unit 2 of the eigenvalues and eigenvectors. So before defining this diagonalization of a square matrix, we will define one more definition, that is called similarity transformation. Similarity transformation means when the given matrices are similar. Suppose we have two matrices. When we say that the two matrices are similar, for example, if A and B are two square matrices of order n, then B is said to be similar to A if there exists a non-singular matrix P such that B is equal to P inverse AP. Then we can say that B is similar to A. And moreover, the similarity of the matrices is an equivalence relation. We know what is the equivalence relation. So we studied in lower classes. Equivalence relations means any relation satisfying the three relations: reflexive, symmetric and transitive. The relation is called equivalence relation. Here the similarity of the matrices is an equivalence relation, means if B is similar to A, means A is also similar to B. And also we have some properties related to the similarity of matrices. The first one is the similar matrices have the same determinant. That means whenever if it is have same determinants, means the similar matrices have the same eigenvalues also. For example, if A and B are two similar matrices, then both have the same eigenvalues. So first we will define similar matrices. Similar matrices. If A and B are two square matrices of order n, then B is said to be similar to A if there exists a non-singular matrix P, non-singular matrix P such that B is equals to P inverse AP. So this is the definition of the similar matrices. We know what is the mean by non-singular matrix. If the inverse exists, we can say that that is a non-singular matrix, and it is denoted by the notation. We will write B is similar to A. So this symbol is called here B is similar to A. So we have some remark. What is the remark in that we have to cover? The first one, the similarity of the matrices is an equivalence relation. Similarity of matrices is an equivalence relation. Is an equivalence relation. We know what is the equivalence relation. Okay, and similar matrices have same eigenvalues. So this is very important. the same determinant also. If A and B are similar means they both have the same eigenvalues. And one more property, if A is similar to B, it means these two are similar matrices, and if X is a eigenvector of A corresponding to eigenvalue lambda, then P inverse X is an eigenvector of B corresponding to same lambda, same eigenvalue, same lambda. So, from this what we have to conclude this one, what tell about if A and B are similar matrices, once you know the eigenvector of A, we can find out the eigenvector of B. Then how to compute eigenvector of B? The P inverse X is a eigenvector of B. Then how to compute this P inverse we will discuss in the coming classes. So, next we will move to the definition of the diagonalization of a matrix. Diagonalization of a square matrix. So, a square matrix A is said to be diagonalizable if it is similar to diagonal matrix. You know what is the diagonal matrix? Be represented by capital D. So, all element except the principal diagonal elements are 0. The matrix is called diagonal matrix. Means just now we defined similar matrices. So, there exists a non-singular matrix P such that P inverse AP is equal to D. Then we say that A is diagonal matrix. A matrix A is diagonalizable if and only if it is, or if we can write, if it is similar to diagonal matrix. Just now we use this notation, it is similar to diagonal matrix. What is the D? Is D represent here diagonal matrix. We know what is a diagonal matrix. It is a matrix except the principal diagonal elements. If all elements are 0, that matrix is called diagonal matrix. Any matrix similar to diagonal matrix, that matrix is called diagonalizable. That matrix is diagonalizable. Or in other way, we can, what is this meaning? That is, if there exists a non-singular matrix P, a non-singular matrix P such that P inverse AP is equal to D. So, this is the definition of the A is similar to D. A is similar to D means there exists a non-singular matrix P such that P inverse AP is equal to D. Here D is called diagonal matrix. Here the matrix P is called model matrix. Model matrix. And the diagonal elements of the diagonal matrix are the eigenvalues of the matrix. Here you will get. So, here how to compute this P we will discuss in the process of diagonalization. Okay. So, next one is the application of diagonalization of a matrix. So, once we define the diagonal matrix, this is over. So, what is the use of this diagonalization of a matrix? So, once matrix is diagonalizable, then we can calculate the power of a matrix very easily. So we can calculate if A is diagonalizable. Suppose if A is diagonalizable means if A is similar to D, then we can compute any power of a matrix A, any power of matrix A. Even you can, if A is diagonalizable, we can calculate e to the power of 100, e to the power of 200, even a power 1000 also we can calculate just multiplying the three matrices. How that process will, I am going to explain now. So, how to find that power of a matrix? Suppose let A be a diagonal matrix and let lambda 1, lambda 2, lambda 3 be eigenvalues. Be eigenvalues. Okay. So, by definition, if A is diagonalizable means what is the definition? There exists a non-singular matrix P such that P inverse AP is equal to D. So, this is from definition I am writing, P inverse AP is equal to D. This is from the definition of a diagonalization of a matrix. Now, find out D square. Then how to get D square? P inverse AP, D into D will get P inverse AP. If you look at this middle, here P inverse is equal to I. If any matrix multiply with identity matrix will get same, then in middle what will get, this one A square will come. So, if you simplify, so what will get? P inverse A square P. So, this is what D square. Even if it's in the same way, even if you compute D cube also will get the same manner, but the effect, if you look at this calculation, the impact is only on the middle one. Okay. So, we will get this one, we can guess easily A cube P. Similarly, D to the power of n, now we can easily guess P inverse, the impact is only on the middle matrix A to the power of n P. Now, our objective is what? Our objective is to find A to the power of n, power of a matrix. So, in order to find that, what we have to do is pre-multiply both side P and post multiply P inverse, both side we have to do. Now, look at here, you have tried this one. Okay. If LHS, look at the LHS, the P D power n, the P inverse. If you look at the RHS, here PP inverse will become I, here PP will become I. So, we will get A to the power of n, the right hand side will get A to the power of n. Now, look at P, we have the P and D power n. How to get D power n? Very simple. If any we have the diagonal matrix, we can easily calculate the power of a diagonal matrix, just rising to the power of the diagonal element we will get it. So, this means here what is the D? D is the diagonal matrix and diagonal elements are the eigenvalues. Compulsory what we will get? Eigenvalues of that one, 0, 0, lambda 2. So, what is the D power n? Just rising to the power of n, 0, 0, 0, lambda 2 whole to the power of n, 0, 0, 0, lambda 3 whole to the power of n. Here you can write the P inverse A to the power of n. Now, if you take any value, if n is equal to n, suppose if you take n is equal to 100, if substitute 100, just multiplying these three matrices will get the A to the power of 100. Even if you take n is equal to 1000 also, we can compute very easily, very simple way, just multiplying the three matrices. So, this is the use of the diagonalization of a matrix. If the matrix is diagonalizable, we can calculate very easily the power of a matrix, but this is valid only for the matrix is diagonalizable. We cannot apply for the non-diagonalization. Okay. So, we will do the problems in the next lectures. Okay. So, next is the concept map for the diagonalization of a matrix. We will give the two concept maps. One concept map is then how to verify if the given matrix is diagonalizable or not, how to check it. Okay. Then second one, suppose if matrix is diagonalizable, what is the process of diagonalization? So, we will give the two concept map. The concept map 1, is the verification of diagonalization of a matrix, of a square matrix. Suppose we have the square matrix. So most of the student will confusing about this verification of the this matrix, if the matrix is diagonalizable or not. But after this concept map, I hope you will understand clearly when the matrix is diagonalizable or not. So for the basic, the logic for drawing this flow chart is the main theorem. One theorem is there. The theorem is called, if a square matrix of order n is diagonalizable if and only if it possesses n linearly independent eigenvector. For example, if A is a 3 by 3 square matrix, so any 3 by 3 square matrix diagonalizable if and only if it possesses 3 linearly independent eigenvector. So finally, it possesses 3 linearly independent eigenvector, the matrix is diagonalizable. For example, A is 4 by 4 square matrix. So finally, it is having 4 linearly independent eigenvectors, it is diagonalizable. The simple way is, suppose we have the rectangular table. In order to make the rectangular table, how many sticks we require? 4 sticks. If we have the 4 sticks, we can form a table. In the same way, a square matrix of order 4, a square matrix of order 4 is diagonalizable if it possesses 4 linearly independent eigenvectors. So what happened if less that one? If less than 4, we cannot form a table. For example, A is a 3 by 3 matrix. Finally, we got only 2 linearly independent eigenvectors. In that case, that matrix is not diagonalizable. So keeping that theorems, I will draw the flow chart of the verification of the diagonalization of a square matrix. So let here what I am taking is ABA, any square matrix, any square matrix, any square matrix. Now this I am dividing into the two categories. One I am dividing to symmetric and non-symmetric. The case one, if A is symmetric matrix, what this represent A transpose symmetric matrix, symmetric. The non-symmetric, non-symmetric mathematical how to write A transpose. This is called non-symmetric matrix. So first what you have to do is now separate symmetric, non-symmetric. By seeing we can easily verify whether symmetric or non-symmetric. How to verify symmetry? Look at the first row and first column. If the first row is identical with the first column, similarly second row is identical with second column, third row is identical with third column, then the matrix is similar matrices. If all rows and all columns, corresponding rows and corresponding columns in the given matrix are identical, then we can say that it is a symmetric matrix, or we can say A transpose is equal to A. We know what is the A transpose, interchange the rows and column. If you get the same matrix, is called symmetric. So every symmetric matrix is diagonalizable. If it's symmetric matrix, it is diagonalizable. Just by seeing, we can tell that if it is symmetric, we can say that we have the theorem also, this one, diagonalizable. Coming to this side, the left side case is non-symmetric matrix. By non-symmetric matrix, we cannot say whether it is diagonalizable or not, may or may not diagonalizable non-symmetric. But when it is diagonalizable, compulsory we need to compute eigenvalues. Find lambda. Hope you understand what is the lambda. The lambda means we are compulsory, you have to calculate eigenvalue. So eigenvalues, may we have the two types of eigenvalues. Maybe eigenvalues are distinct, eigenvalues are not distinct. Let us say, for example, A is a 3 by 3 matrix. So A have 3 eigenvalues. Category 1 first I am taking, if the 3 eigenvalues are distinct, let us say A, B, C. For understanding, I am taking 3 distinct eigenvalues. If eigenvalues are distinct, it is diagonalizable. So we have the result also on this one. If any square matrix having distinct eigenvalues, it is always diagonalizable. So this means diagonalizable. But coming to the eigenvalues are not distinct. Not distinct. What is the meaning of not distinct? Eigenvalues may be repeated. In that case, we cannot say, from observing this, we cannot say whether the matrix is diagonalizable or not. Compulsory, we need to compute next step. Next step means the furthermore step. What we have to do is find eigenvectors. Find x. Hope you understand what are the x eigenvectors. So eigenvectors, again we have the two cases will arises here. The number of eigenvectors equal to order of matrix. Order of matrix. The second case, number of eigenvectors less than order of matrix. So whenever if you number of eigenvector in the repeated case or repeated eigenvalues, if number of eigenvector equal to the order of matrix, diagonalizable. In this case, but if number of eigenvector is less than order of the matrix, is not diagonalizable. So this means it is not diagonalizable. Very simple. Once again, just I quickly review that one. First, what we have to do is, if the matrix is given, first look at whether symmetric or non-symmetric. If it is symmetric, we know every symmetric matrix is diagonalizable. It is diagonalizable. Suppose if non-symmetric, we cannot say by saying we cannot whether it is diagonalizable. Compulsory, we have to find eigenvalues. So here eigenvalues, we have the two types of eigenvalues. Nature of the eigenvalues. The type 1 is what? If all eigenvalues are distinct, diagonalizable. Why? Because we have also, this is theorem on this one. If eigenvalues are distinct, if all eigenvalues are distinct, the matrix is diagonalizable. But if eigenvalues are not distinct, means repeated, in that case may or may not diagonalizable. Means how we will conclude? We need to compute furthermore step. The furthermore step is we have to find eigenvectors. We have to calculate eigenvector. After calculating the eigenvectors, finally look at how many eigenvalues you got it. Then you compare with the order of the matrix. If the number of eigenvectors equal to the order of matrix, in that case the matrix is diagonalizable. Suppose if the number of eigenvectors is less than order of matrix, in that case the matrix is not diagonal. For example, if A is 3 by 3 matrix, so finally if A we got 3 eigenvectors, therefore it is diagonalizable. Suppose A is a 3 by 3 matrix, finally we got 2 eigenvectors, it is not diagonalizable. Why? Because the number of eigenvector is 2, which is less than its order 3, therefore it is not diagonal. So this is the concept map for what? Verification of the given square matrix is diagonalizable or not, just whether it is yes or no, whether it is diagonalizable or not. From this concept map we can easily verify that whether the given matrix is diagonalizable or not. In the next class, what we have to do is, if it is diagonalizable, what is the process of diagonalization? We'll discuss in the next class. So today I am ending the session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.